Did you hit it? Oh, okay. I couldn't hear the beep as we discussed. I don't hear the beep. It's unnerving for me. I will begin with a word of prayer. So, what is it? You look perplexed.
No, I mean,
Oh, okay. I will pray. I will pray. Dear Heavenly Father, we thank you for this day again, Lord. I thank you for these students, most of them, and just pray you be with us today. Help us to glorify you, would you, Lord? In your name I pray. Amen. Okay, so just a I think we're okay with the lights on. So, if you have an eigenvector, oh, thanks though. It's fine. It's good. If we have an eigenvector, right? An eigenvector, in other words, a times uj is like, lambda j uj. So we have an eigenvector u sub j for a. Then it's easy to prove that if you look at e to the lambda jt times uj, then this gives us a solution to the differential equation x prime equals to ax. The proof of this, you could just plug it in and see that it works. So like, if I differentiate e to the lambda t times this constant vector uj, well, the derivative of the exponential, this pulls out as a constant vector, so the differentiation goes component-wise. You can pull out constant vectors. It's part of the calculus here. And then the derivative of e to the lambda j times t is just lambda j times e to the lambda jt. But then you can pull this scalar out. You can lambda j times uj is equal to a times uj. And then you put the exponential function back with u again, and then you're back to x again. So this line right here shows you that dxj dt is equal to a times xj, which is the same as saying that this function right here is a solution to the differential equation. So every eigenvector that you can find for a matrix gives you a solution to the corresponding differential equation x prime equals to that matrix times x again. So when you're looking to solve differential equations, the first thing you can do is just look for eigenvectors. By the way, if you find a complex eigenvector, then it turns out you can take the real and imaginary parts of the complex solution, and those are separately real solutions. You can prove a little theorem that anytime you have a complex solution to a differential equation that looks like x prime equals to ax, if like you have z prime equals to az, the real part of z and the imaginary part of z are separately real solutions to that differential equation. Anyway, that's a later section in this chapter. So I'll just look at a specific example. X prime equals to x plus y prime equals to 3x minus y. When we translate that into the matrix normal form, it looks like this. And so then we can look for eigenvectors and eigenvalues. It turns out that the eigenvalue of this matrix is -2 with eigenvector -1, 3, or eigenvalues -2 or then +2 over here with eigenvector 1, 1. So using this derivation I just did, here's the solution, constant times the first solution plus another constant times the second solution. This is the general solution to this differential equation. And so you notice we've done all of this without so much as a nod to geometry or anything, right? It's just an algebraic technique. But you might ask the question, like, what does this really mean? Like, what are we actually doing besides just being an algebraic technique? Like, what's really going on here? Can you visualize this? And you can. I have a picture down here. So the other way you could look at this is a coordinate change problem. You could change to the eigencoordinates. P is u1, u2, and you'll notice I have clearly marked P inverse AP here. See, right there, P inverse AP.
Oh, that's nice.
There's apparently a very damaging place where I put PA, P inverse, and you guys have read too much into it, some of you. Sorry about that. It's on my list of things to fix. Anyway.
There are a bunch of places where you put the beta and beta inverse matrices in the wrong order, and John and I were confused by that. But
I would like a list of those. I could fix those Esperanto. Yeah. Yeah, when you, of course. So, let's see here. So, if I can diagonalize the matrix by doing. So I mean, sometimes PDP. This is not wrong. I mean, it's just that I've solved for A instead of P. So some of these PA, P inverses. I mean, sometimes the P P inverse being in the opposite order is because I'm not diagonalizing it. I'm sort of undiagonalizing the diagonal matrix to get back to A, like this expression right here. I'm writing A in terms of the diagonal matrix and the product of the basis matrix and its inverse. All right? But anyway, if you just look at this differential equation and you translate it in terms of the eigencoordinates, this is, again, P inverse times dx dt is equal to, this is, well, I mean, I start with dx dt equals ax, but a is that. So then if I multiply this differential equation by P inverse on both sides, it gets me to this. But P inverse is a constant matrix, so I can bring it inside the derivative, which gives me that the derivative of P inverse x dt is equal to d P inverse x. Now, this right here is the coordinate vector of x with respect to the beta basis. In other words, it's the eigencoordinates. And this, again, is the eigencoordinates. So what this shows you is that if you translate to x bar, y bar being the new coordinate system with respect to the eigenbasis, the differential equation, which was originally coupled, now decouples into dx bar dt equal to minus 2x bar, and dy bar dt equals to 2y bar. So the formulas are vastly simplified in the eigencoordinates. Now these, you can solve one at a time, separate and integrate, calculus 2 style. Solution is immediately x bar equals to c1 e to the minus 2t, and y bar equals to c2 e to the 2t, using calculus 2 stuff. And so, that's what the eigencoordinates are doing. If you actually pursue the coordinate change, which is suggested to you by eigenvectors, if you actually put that into practice, it gets you to this uncoupled system, which you can solve one at a time without anything fancy. And yet, you can solve the system without doing that, right? I mean, I showed you at the start of the lecture that we can just find eigenvectors, we find eigenvalues, and we follow the procedure, write down the general solution without so much as a coordinate change, right? But there is coordinate change in the shadows. Here's a picture of it. These are solutions to the differential equation, x plus y, 3x minus y. And these directions are the eigendirections. So this is like the y bar axis, this is the x bar axis. And so the solutions are kind of flowing. Those are asymptotes to all the solutions. So there's so many things you can see if you start digging into the details of a specific example. All right, enough about that. So the matrix exponential, let's get back to it. I defined it last time for you guys. Here's some analysis I'll skip over. These are things you can prove about series of matrices. You can pull out scalars. The sum of series is the series of the sum. You can differentiate term by term. You can integrate term by term, given that the series of matrices is what's called uniformly convergent. You can ask Dr. Scambortis what that means. Or take advanced calculus. I'll explain a little bit more. Anyway, so long story short, this is what we worked out last time. Remember, the derivative of the exponential is a times the matrix exponential again. So it's a solution matrix, right? So like I said, every column in the matrix exponential is a solution to the differential equation. If you have A as a diagonal matrix, it's pretty easy to calculate the kth power. What's the kth power of a diagonal matrix? You just power the diagonal, it turns out. And so I can actually calculate the matrix exponential directly here by just doing each. So that's e to the t. This is e to the 2t. This is e to the 3t, calculus 2. So the matrix exponential is the matrix of the exponentials in this very special case. Usually it's more complicated how a raised to a power works, right? Most matrices are not diagonal. This much we can say, if the matrices A and B commute, if A times B is B times A, something really nice happens for the matrix exponential. We get the ordinary law of algebra for the product of matrix exponentials. Here's the proof. E to the A times e to the B, to second order. To prove this in general is not simple. 1 plus A plus 1 half A squared, da da da. 1 plus B plus 1 half B squared, da da da. And we multiply this, collect terms. There's your constant term. This is the identity matrix. Linear terms, you got 1 times A, B times A plus B. Quadratic terms, you got this 1 half A squared times 1. You got this 1 times this 1 half B squared. You've also got A times B and Yeah, that's it. That's the only quadratic terms in the product of these two series. So that's it up to quadratic order in A and B. On the flip side, you can square A plus B. A plus B squared is A plus B times A plus B, which is A squared plus AB plus BA plus B squared. You notice we can't commute A and B generally, but in this case we can, if we're assuming that, right? So this is 2AB plus B squared. So when I look at the exponential e to the A plus B, that would be like 1 plus A plus B plus 1 half A plus B squared, right? And so if I divide by 2, I've got 1 half A squared, I've got AB, I've got B squared. These terms match. Those terms match, right? And so that proves that this exponential is equal to that exponential up to quadratic order. I was going to make this a homework problem for you guys, but I just don't think it's that important to you. I wanted you to see that it's true, but I mean, you could work it out to third order for kicks if you want. So here's the commutator is sometimes interesting to study. This is a typical notation. A bracket B is AB minus BA. So to say that matrices commute is to say that their commutator is 0. And the commutator has all kinds of neat properties. These make great homework problems. I think I've assigned you none of them. If you want, I can add one to the list. Would that be, I don't know, it's just extra credit? All right, I will add one of these as an extra credit homework problem. Yeah. So sure, why not? Now, it'll be on the next mission, which I'm currently writing. Anyway, so here's what's generally true. E to the A times E to the B is E to the A plus B plus 1 half the commutator of A and B plus 1/12 the commutator of A and B with B plus 1/12 the commutator of B and A, comma A. Now, I'm not sure about these signs actually. I probably should put plus or minus here. I never remember. And it keeps going. Like the next terms I haven't written are commutators of commutators of commutators. And it gives you this infinite series of nested commutators, getting more and more and more nested the further you go out. But what's interesting about this is that means that if you know how the commutators work, that tells you how to multiply these kinds of objects. All right? So it turns out that specifying the values of commutators is given by what's called a Lie algebra. And the exponential of something in the Lie algebra is something in what's called a Lie group. And this actually shows you how you multiply things in the group by the rules in the algebra. Anyway, this is important to modern physics, which is all about Lie groups and the algebras in part. So I'll shut up about that. Here's a kind of more interesting thing that you could maybe appreciate. I found this formula, to me this was deeply satisfied when I first saw this. You can write Taylor's theorem as an exponential of an operator. So if I write exponential of h times the differentiation operator, what is that? It's 1, right? Plus what? H d dx plus 1 half h squared d squared dx squared and so forth. So, so if I have e to the hd x on f of x, and so this is differentiate and then is what I wrote. So if we do that, we get f of x to start with, right? We get h times f prime of x is our next term. We get 1 half h squared f prime prime of x is our next term, and so forth and so on. This is exactly the Taylor expansion at x of f of x plus h. Oh, well, I thought it was cool. I don't know. This was also almost a homework problem for you. So yeah, we can, I think I proved this last time though. So let me go on. Another thing that's true about the matrix exponential is the determinant of the exponential is the exponential of the trace. Which is, I mean, this is an ordinary exponential. This is a matrix exponential. This is a connection between the ordinary exponential and the matrix exponential. It's kind of surprising, I think. Yeah? So if you could turn the lights back on here for a second. Thanks. Something I haven't emphasized enough yet to you guys, and I think this is a good place to do it. So we found that the matrix has a Jordan form, right? So basically, let me focus on a single block, because these comments apply just as well to a larger thing. But suppose we have a single block, like lambda, and I'll just do a 4 by 4 is big enough, right? So this would be what in our language? This was a, what is this? This is, right, this is J4 of lambda in our current lingo. Now, you can rewrite this as a diagonalizable piece plus what's called a nilpotent piece. All right? So I'm saying I can rewrite this as the sum of two matrices, a diagonal one plus a nilpotent one. Can you tell me what those are?
Lambda part and the superdiagonal part.
Right. So this is lambda times the identity, 4 by 4 identity, and then the superdiagonal part. Yeah, exactly. Which I don't know, I might call this like N4 or something. It's sort of the fundamental nilpotent 4 by 4 matrix or something like that. Yeah, so it's pretty easy to see that d times n is equal to n times d. Agree? I mean, d is a scalar multiple of the identity matrix, so it commutes with everything. That's not hard to check. But those matrices commute. And so if I look at e to the d plus n, what is that? Well, e to the a, right? Equals e to the d plus n, right? But these commute. So that means this is e to the d times e to the n, right? And hey, let's multiply it by, I'll multiply it by t so it's more relevant to what we're actually kind of focusing on here at the moment. So t, 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 t. All right, there we go. This, remember we just looked at the 1, 2, 3 matrix. The exponential of 1, 2, 3 was e to the, so this is just what? E to the lambda t, e to lambda t. Well, I mean, I feel stupid to write it. If you don't mind, this is e to the lambda t times the 4 by 4 identity matrix, right? That's what this is. Because it's e to the lambda t on the diagonals. Just like our 1, 2, 3 example. And what's e to the tn? What do you get to say about this? It has degree 4, right? N to the 4th. Let me just call it n. N to the 4th is equal to 0, right? What's n cubed? Well, here. I'm out of space. I'll just write them here. So that would be what? That's the identity plus t times n, right? Plus 1/2 t squared n squared plus 1/6 t cubed n cubed, right? And that's it. Because all the higher terms in the matrix exponential are gone. So you see, if we have the Jordan form for the matrix, it's relatively simple to calculate the matrix exponential directly. Right? We have the exponential, and you can do this block by block too. Right? This story would play out on each block. If you had more blocks, you have to kind of put things together, but whatever. This n squared is what? The way this multiplication works is you can kind of imagine these sort of just going up like that and kind of vanishing off the corner. So like n squared is 0, 0, 1, 1. See that? So you can imagine this row of ones just kind of, the super diagonal ones becoming a super diagonal. And then n cubed is 0, 0, 0, 1, 0, 0, 0, 0. And now it's like super, super diagonal. And there is no super, super, super diagonal. I mean, you're off the grid after the next power. So it's a neat pattern to look at. This, if you have the super diagonal ones, when you power it up, it just pushes that up like that. If you hadn't noticed that already. So anyway, that's how we can calculate the matrix exponential. And I basically use that here to argue that if you have A, you can, I guess you're going to hit the lights again, thanks. If we have A, we can, there's a similarity transformation to the Jordan form, right? And so with respect to that, we have P e to the d, e to the n, P inverse. And so the determinant of the exponential is the determinant of these, but by properties of the determinant, the P and the P inverse cancel, and you just have the determinant of e to the d and the determinant of e to the n. But you can pretty easily calculate that these are strictly upper triangular, right? So if you look at e to the n, it's just ones down the diagonal with stuff above the diagonal. So the determinant of that is the product of the ones, it's just 1. The determinant of this is 1. And the determinant of that is e to the lambda 1 times e to the lambda 2 times e to the lambda 3, because it's exactly the diagonal matrix with e to the lambda, e to the eigenvalues down the diagonal. And so if you have e to the lambda 1, e to the lambda 2, da da da, e to the lambda, however many you have, what is that equal to? Yeah, lambda 1 plus lambda 2. I really should be telling this to calculus 3. They're a little shaky on this right now. Let's see here, e to the trace of A, because the sum of the eigenvalues is the trace. So this is the determinant of e to the A, and it's e to the trace of A. So anyway, this is the kind of theorem you can prove. There's a lot of questions that would be very difficult to answer without the Jordan form. Jordan form is just like very concrete, general sort of shape you can push your matrix into, and you can make arguments on it. That would be very difficult if you just used the matrix without this kind of structure. I have 2 other proofs in the notes for that. I'll let you look at them. So this is the magic formula. I told you guys I'd explain it today. So I think we have all the tools we need now to understand it. If I have e to the ta, what I do is I just add and subtract t lambda I. That's 0, right? But then the cool thing is this matrix, t times a minus lambda I, and this matrix, t lambda I is a scalar multiple of the identity. Which matrices does that commute with? Exactly. So you have identity matrix times a number, it will commute with everything. So we get the laws of exponents for this sum because that's a scalar multiple of the identity. And so I have that this is exponential of the first thing in the sum times the exponential of the second thing in the sum. But hey, we've got e to the diagonal matrix. So that's the diagonal of the exponentials. Just like the 1, 2, 3 example at the start. So that's e to lambda t times I just don't write the I. And then I'm still left with this, but then I just go back to the definition of the matrix exponential and unfold that as a power series. So we've got I plus t times a minus lambda I, and so forth and so on. And this is what I lovingly refer to as the magic formula. All right? Again, this is significant because we proved last time the matrix exponential is a solution matrix to the differential equation x prime equals to ax. So if you have this, and you can kind of extract things from it, then you got solutions. Let me show you how. We don't need quite all this jibber jabber. Let's see here. So here's basically the thing that's so cool. If we have a chain of generalized eigenvectors, v1 through vk, so that means that, what's that mean? That means that a times a minus lambda I. There's an I missing here. Sorry about that. And here too. Oh, man. I mean, it's not a... I don't know. I'd debate whether or not you really need to write the I there, but fine. You guys, what do you think? We had to put the I there? We have to put the I there. Man.
I mean, what problems do we run into if we don't?
The student's complaining, so it's a problem. Let's see here. So a minus lambda I times v1 is 0. That makes v1 an eigenvector. And of course, these are generalized eigenvectors, right? I mean, so vk is the generating one. If I start with this and then I multiply by a minus lambda I repeatedly, I will get vk minus 1, v2, and times v1. I mean, I'll generate the whole list from the top one. Anyway, so this is how the eigenvector works. E to the ta times eigenvector gives me e to lambda t times v1. If I have a generalized eigenvector of order 2, I get e to lambda t times v2 plus tv1. Order 3, I get v3 plus tv2 plus 1/2 t squared v1, and so forth. So this means that anytime I have a generalized eigenvector, I multiply by the matrix exponential. It truncates at finite order because of the magic formula, and I have a specific formula built from the eigenchain. Yeah.
Is that backwards? The a minus lambda vk minus, shouldn't that be you multiply by vk and that gets you vk minus 1?
Oh, yes. I'm sorry. Yes. Flippity floppity. Yes, indeed. That should be k and k minus 1. Oh, my goodness. Ah, I need a refund, whoever wrote these notes. Let's see here. Some idiot. Here's the proofs. Let's just look at one of them. Let's look at this one. So e to the ta times v2. All right, so v2 has a minus lambda I squared times v2 is 0. And if a minus lambda I squared times v2 is 0, that means the cube and everything's 0 from this point on out, right? But on the other hand, a minus lambda I times v2 gives me v1. Thank you, Zach. Not the other way around. So that gives me v1, and this gives me v2. So there's the formula, e to lambda t v2 plus t v1. So once you have a Jordan basis, it's really easy to solve the differential equation corresponding to that matrix. You just write it down from the magic formula, what I'm showing you. Let's see if I have an example. Oh, tigers eating bunnies. Yeah, of course, why not? Let's see here. Here's one. Uh-oh, a missing example. Oh, no. Excuse me. So this is a matrix in Jordan form, which is nice. If the matrix is in Jordan form, the standard basis is a Jordan basis. This is relevant to your homework, yes? So like I can look at this matrix and I can tell you, eigenvector. E1 is an eigenvector with eigenvalue 1. E3, eigenvector with eigenvalue 1. E2 and E4 are generalized eigenvectors of order 2. Like this E2 will generate E1 upon multiplication by A minus I. Anyway, these are things you hopefully will discover as you do the homework. Anyway, so long story short, we have A minus I U3 is U1. What? Oh, man. Come on. Really? I mean, I agree with this one. What is U1?
You say right below. Uj equals ej.
Oh, yeah, there's a most annoying typo here. That's supposed to be a 2, right? Okay. And this one here, that should be a 4. This should be a 3. Okay.
And then that 2 should be a 3.
That 2 should be a 3. I don't know.
That's very odd.
It is odd. I think these are right. Yeah.
It's like you ran a search and replace on that one section. Just for 2s and 3s.
Maybe I had a different example and then I changed the example, but then I didn't change all of the example. That's most likely what happened. Anyway, you should read my notes critically. If you get confused, should you spend an hour thinking about this? No. You should spend like 5 minutes and then you should send me an email. And the email could be just like this. In example 9.5.8, I can't make sense of the numbering of the u's. Could you look at it for me? I'd be happy to. Just send me the email. Do not labor in your indecision, right? Does not impress me. I spent 3 hours, I couldn't understand. Email me. I'm almost always available by email, many times available by email. Often, answering your email would be infinitely more interesting than whatever else I happen to be doing at that time. Right? Not holding my baby. Holding the baby is interesting. I'm talking about like administrative paperwork. Okay, so anyway, so long story short, I'm digressing, obviously. E to the at times eigenvector gives me e to the t e1, because the eigenvalue is 1. X2, magic formula pops out this t term. So I get e2 plus te1, and then te3 because it's an eigenvector, and then e4 plus te3 because it's generalized eigenvector order 2. And so that's how you solve it. So what about the complex case? Right? I mean, I have oodles of examples. Hopefully they're not so error prone. Hey. Well, if you find them, let me know. Yes, please. Thank you. Maybe I should just make that the homework for this semester. Find all the errors in my notes.
I refrain from doing that because it's been changing a lot.
Or it could be a great extra credit.
So I just skipped past the non-homogeneous problem because I'm not covering it this semester. So you can skip it if you want to. You know, the question is, what if you have dx dt equals to ax plus f, where f is non-zero? That's a non-homogeneous problem. I cover that in differential equations if you want to see it there. Okay? I won't do it in here. It's in the notes, though. Sorry about that. So what if you have what if A has complex eigenvectors, right? So there's the complexification has eigenvectors with eigenvalues lambda, where lambda are complex. Thinking of A here being real again. So, you know, you could suppose you had a chain of generalized eigenvectors, complex eigenvectors, v1 through vk. In that case, these would be complex solutions. The magic formula still makes sense. You still get the same structure for the complex eigenvectors. But then the thing is, they're complex solutions, which means that every complex solution has 2 real solutions. So all you do is you take these and you rip them apart into their imaginary and real parts, and those give you the real solutions. So like this one, it gives you 2 things. It gives you the real part and the imaginary part. The real part happens to be this. The imaginary part happens to be that. That's nothing more than just writing v1 as a1 plus ib1 and expanding this in terms of Euler's formula, e to the alpha t times cosine beta t plus I sine beta t. So I don't know. There may be a homework. You can appreciate it more there. I don't really want to say more about it here. It's not too central to what we're doing. Here's a specific example. So if we look at the matrix 0, 1, minus 1, 0, we find that the eigenvalues are plus or minus I. Of course, those are complex eigenvalues, right? And the complex eigenvector is 1i. So we have real part of the vector is 1, 0. The imaginary part of the vector is 0, 1. That's the a1 and b1 in the theorem I just looked at. And so this is the real part of e to the it times u1. It's cosine times that minus sine times that. The I times I gives you a minus 1 in Euler's, from the Euler's identity. And there's the other piece, the imaginary part of the complex solution. So I think this is what I'm showing you, shows you how to solve x prime equals to ax for any real matrix. This is a completely general solution technique brought to you by the Jordan form and magic formula. And also the thing I didn't prove, which is that for every A, there exists a Jordan basis, right? I've given you a lot of evidence that it must be true, but I didn't really prove it. Nor will I this semester. So anyway, that's about it for this stuff. I think I've given you enough that you can do the homework on this stuff. I hope. Yeah. I foolishly hit that button. I can't hear you.
Do we have the same rule for block diagonal matrix?
Block diagonal matrix, same rule. What rule?
Like an exponential rule apply for diagonal matrix?
The exponential. Does the exponential behave nicely with blocks? Are you asking if we have,
Differential of that monometric, you just take
so you're asking, is this an identity, I think? That is a good question. Extra credit homework question number 2. Very good. All right, so I'll add that to the next one. Do I have to write solutions to these? Oh, what am I doing?
You'll get bonus points too.
I'll get bonus points too. I'm pretty sure the only way I get bonus points in classes is from taking away homework, not adding it. Rate my professor. Yeah. Still waiting for my chili. It's here. Man, I haven't looked at Rate My Professor in a few years. I don't know. Every once in a while, it's fun to look for all the wrong reasons. Okay, so I should admit to you, yeah, I never can tell, but this is, as you can see, linear algebra. Circulation of this edition outside Indian subcontinent is unauthorized.
Outside what continent?
Supreme Court says otherwise. Ah. Take that, Pearson. Sorry. Although, if you do buy this, beware, they have unceremoniously cut off the final and most important chapter. This book is missing 100 pages of its true form. Yeah. In fact, the Jordan form chapter is missing. It's exactly that one. So, I know it is. I covered it so excellently. Poor Jordan. Yeah, Jordan did okay. Jordan actually was like one of the preeminent group theorists, abstract algebraists, really, of the 19th century. He was a deep and non-trivial mathematician. I mean, he gave us the Jordan form, right? But
Is it the same Jordan as Gauss Jordan, or
I think so.
that would make sense?
That would make a lot of sense.
I do think it's the same as Gauss Jordan. Okay, so anyway, what I'm telling you is I'm currently in the process of translating this book to my notes, right? So pretty much I'm just going to steal all the theorems in this book in chapter 6. I mean, that's what I do. This is, you know, I mean, I'm not talking about something uninteresting. I'm talking about math. We share it. You know, I mean, these are not their theorems either. So this brings us to the discussion of inner products. This is chapter 6 in this book. Although I don't expect you get it, I expect I write notes. But obviously, well, here we are. And at the moment, all the notes have in it is the first definition. But that's a good place to start. Definition. V, a vector space over F. All right. An inner product on V, goodness gracious. Inner product on V is a function from the Cartesian product of V in itself to the field, denoted x comma y maps to Langle x, y wrangle. There's a LaTeX joke there for you. Let's see here. Anyway, we have the following axioms. A, the inner product of, so this is read inner product of x plus z with y is, you guess. I'm going to let you guys guess the axioms here. Inner product of cx with y is equal to, you guess it, c, the complex conjugate, oh no. Now, Sam has told me that I have not lived up to my own legalism on this topic here. There's someplace I claim I'm going to not use the notation star.
Only one place.
Only one place? Oh, well, that's pretty good.
Same page as
That's actually somewhat surprising given my other transgressions we've seen today. But although I didn't spend as much time looking at the differential equations chapter as the other one. Okay, so what do you guys think?
X and y plus c and y.
Yeah, x comma y plus z comma y. So it's additive in the first slot. That's the language I would tend to use for that. Additive in the first slot. How about this? What do you think? C? All right, I have a vote for C, x comma y. We have, in fact, that is true. How about this one? What should the complex conjugate of?
Conjugate of x, comma y.
In fact, no, it is yx. That one's kind of hard to guess. Let's see here. So the inner product of x with itself is positive if x is not 0. There are other ways of stating the fourth axiom. They're basically the inner product of x with itself is 0 if and only if x is equal to 0, and the inner product of x and x is non-negative. I mean, I've seen a lot of different ways to state that. This is a pretty good way to state D. It's called positive definite. Okay, so this right here is positive definite. So what does this say? I'm going to distract you with toys. Let's see here. What does this say then? Well, so this is the axioms. This is inner product. So can you guys give me any examples? By the way, first comment is, for us, this is either going to be the reals or the complexes. That's pretty much all we're looking at, okay? Sorry to be boring. Maybe some of you want to do like other things.
Are you sure of complex? Because we cannot have ordering on complex numbers.
So that's saying that this is real.
So it's not.
This is, well,
You said that not actually some.
I don't know, but if it's another field, I still have to have some way of complex conjugating that field.
Yeah, but the complex number is not itself like ordering. Like you cannot have a total order.
No, but that doesn't matter because a more complete statement of D would be that the inner product of x with itself is a real number and it's positive. But if you write this, right?
No, because you said it is a function of v squared.
I know, but I can't meaningfully write x with x is positive unless this is a real number. This is a sneaky way of saying that x with x is a real number. Now, this is not the kind of argument you can make to Dr. Skibordis when you don't make your hypothesis clear. But this is the kind of argument you can make to why I don't want to write more than my definition. But I know what you're saying. In principle, I should say that this is real and positive. Yeah. But anyway, so we're just looking at either the reals or the complexes here. That's it. So a lot of times, many of the examples we're interested in are real. How does this definition change if it's real? If V is a real vector space. Then this definition is a little bit easier. We get C translates into xy is equal to yx, right? Which is just called symmetric. It's a symmetric inner product. And what else? I guess that's pretty much it. So examples. Can you guys give me any examples of this? Tell you what, I'll give you examples. Example 1. V equals to Rn. Right? You can define the inner product of x and y to be x dot y, right? Or for those of you who like matrix stuff, X transpose Y. There you go. Example 2. How about Cn? I mean, it's the dot product satisfies these properties, right? You're like, we're not sure. We need a homework on that. That would be a smart question. Let's see here. Here, ZW. Now, in Insel, Spence, and Freeburg, they actually would use the notation Z dot W, but I think that's a little bit dangerous because students might be tempted to think that that's just meaning Z1W1 plus Z2W2 plus Z3W3. That's not what it is. Because you need this condition here isn't that. So there's a couple different formulas for this. Here I'll write one out in gory detail. It's Z1 W1 bar plus Z2 W2 bar plus da 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 plus Zn Wn bar. Or these are complex conjugates. Can you guys tell me how to rewrite that as a column matrix multiplication? I mean a row column multiplication? I mean, here's one obvious one. We could do Z transpose times W conjugate, right? The row of Z's times the conjugate column of W's. What else could I do? I mean, you could just as well look at this as W1 bar Z1, right? I don't know why, but I see this. I mean, from this formula, in my thinking, this shows me W bar transpose times Z. So this is 1 by n times n by 1.
Can you say Z dot W bar?
No. You can't say that because you shouldn't say that because some people use this notation for this. And then that would confuse that.
That's actually how we should take the dot product notation to be.
My suggestion here would be just not to do that. Yeah. I would go with this for the reasons we just uncovered. Now, so can you let's see here. Example 3. Oh, can you see why that's positive definite before I go on? Where am I? Oh, there it is. Right. If we look at ZZ, we've got like Z1 conjugate plus Zn conjugate, right? Which would be like x1 squared plus y1 squared plus da 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 plus xn squared plus yn squared if we let zi be xi plus, j, I, yj, right? So like that's the modulus squared of the first component plus the modulus squared of the second component plus da 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 plus the modulus squared of the nth component. So it's the sum of squares of real numbers. Of course it satisfies this. And the only way it can be 0 is if every component is 0. I should have left that as a homework problem for you guys, shouldn't I? Man, dang it. I'm going to stop wasting your homework problems here shortly. Example 3. What if we do, say, Cn by, we'll start with the reals. Rn by n, matrices. So I think the natural thing to do, if you have like aij times bij like that, the natural thing to try is to just think of them as like really long vectors just strung out, right? And so like that formula would give you a11, b11 plus a12, b12, plus ann, bnn. There are n squared terms, yeah?
This is what you notate with
Asterisk? Oh no, we're not there yet. That would be this right here in the other notation. This would be W asterisk. Asterisk, I can't say that. It's that. In physics, this is typically denoted W dagger Z. This is the Hermitian transpose, or Hermitian conjugate. I will not use the dagger notation in here, except just this once. Okay? I'm going to try not to. Fun. I mean, so that's just natural, right? Like if I ask you the inner product of two 2x2 matrices, you just do like 1 component times 1 component, the 1 2 times the 1 2 plus the 2 1 times the 2 1 plus the 2 2 times the 2 2, and that's the inner product. Just
It's like using the lexicographic basis.
right. But here's the thing that's amazing. This is equal to the trace of a AB transpose, I think. So it turns out that there's a really slick formula for that. This is called the Frobenius inner product. Frobenius was every bit as great as Jordan. He's maybe the first person to really write a genuinely n-dimensional linear algebra book. His work is deep. And then example 4, and we'll be done. If we look at the polynomials, if we replace this with star, that gives us the inner product on complex matrices. Just replace the transpose with the Hermitian conjugate, or the Hermitian adjoint, I should say. Next example, if we look at polynomials over the reals, all right, which I usually denote what? Rx, like that, right? There are many choices, but here's one. F of x, g of x is equal to the integral from 0 to 1, f of x, g of x, dx. This is an inner product. And you could restrict it to, say, polynomials of a particular finite order if you wanted to. You can easily check that it's linear, it's symmetric, it's additive, you can pull scalars out, it's positive definite. The only way you can have an integral of a function with itself from the interval 0 to 1 to be 0 is if it's the 0 function. Right? You can't integrate a function times itself and get something non-zero unless, get 0 unless it's the 0 function. Oh man. But I think I'm going to make these homework problems to actually, at least some part of them, to actually go through and check the axioms for these so you can kind of take ownership of these examples. These are our fundamental examples, pretty much it, of inner product spaces. So anyway. Oh, I'm sorry. I seem to have gone over. I'll make up for it with pizza some other day. How about that?
Going kayaking?
No, never.
Give you.